Hi learners. So till now we are familiar with what is control system, what are various types of the control system. Now whenever we want to do the analysis of the control system, then the first thing that we need is the model. And basic model of anything, that is the physical model. Like model is simply the true replica of the actual thing. So if we just talk about the physical model, then globe is the model of the earth, in case we talk about the physical model. But when we want to do the mathematical analysis, then simplest of the model is the differential equation model. But in the case of the control system, we have two more type of the models, that are the transfer function models and the state variable models. So within this lecture, we'll be studying about the transfer function model in details. So let us start. So as I've already said, that when we talk about the mathematical models, the simplest is the differential equation model. But what is the problem? That it is very difficult to get the solution of the differential equations. So we go for the simpler model, that is the transfer function model, that has been shown over here at the third number. Then in the case of the transfer function model, we have to make two assumptions, that it is valid for only linear time invariant system, and it is, when we are using the transfer function model, we have to make up the assumption that initial conditions are zero. So but it is not true always, so we go for the state space modeling of the control system, that is shown over here. So let us start up with the transfer function model. So first of all, we start up with the definition of the transfer function. The transfer function of a linear time invariant system may be defined as the Laplace transform of the output to the Laplace transform of the input, this ratio, assuming initial conditions to be equal to 0. So it is given, it is represented by GS, and this is Laplace transform of output to the Laplace transform of the input, assuming 0 initial conditions. So this transfer function definition can be directly related to the impulse response of the system. We know that the unit impulse signal is defined as delta t equal to 1 when t is equal to 0, and this is equal to 0 when t is not equal to 0. It's just clear over here that its value is 1 at t equal to 0 and it is equal to 0 otherwise. So if we take up the Laplace transform of such a unit impulse function, it comes out to be equal to 1. So if we just take up this system to which a unit impulse is being applied, we know that GS is equal to CS divided by RS. GS is the transfer function, CS is the Laplace transform of output, RS is the Laplace transform of the input. So since RS is equal to 1, in case unit impulse input is applied, in that case CS will become equal to GS. So it means that CS is what? The output of the system when a unit impulse signal is applied to it. So it means that CS is representing the unit impulse response of the system, and GS is what? Transfer function of the system. So out transfer function of the system is equal to unit impulse response of the system. So that is the relationship. That it can also be transfer function is defined as the ratio of Laplace transform of output to the Laplace transform of input under 0 initial condition, but it also can be defined as the unit impulse response of the system. Then how do we determine the transfer function of a control system? First of all, we'll write the differential equations for the system. Second step is take Laplace transform of the system equations assuming initial conditions as zero. Zero initial condition is the basic assumption while calculation of the transfer function. And when we are taking the Laplace transformation of the system equation, we are simply converting the differential equation to the algebraic equation. Once we have the system dynamics that is represented in terms of the differential equation, then it is converted to the algebraic equation in the second step. Then we just specify system output and input, because when we are taking the transfer function modeling, then we have to consider system to be the seesaw, that we can take only one input and one out. Then from the equations, we just take up the ratio of the Laplace transform of the output, because when we'll be taking the Laplace transformation, then we'll get the Laplace transformed variable. So we can solve these equations, we can get the ratio of the Laplace transform of the output to the Laplace transform of the input as the transfer function. This can be obtained from equations of the step 2. So we can get the transfer function of all the type of the system by using this way. Means first of all, represent the system dynamics in terms of differential equation, then take Laplace transform, then solve the algebraic equations and get the ratio of the Laplace transform of the output to the input, that is the transfer function. Now, to get the transfer function of an electrical system, first of all, we draw the given electrical system. Wherever we are having the resistor, we'll just take it to be R. In case we are having the inductance L, it will be replaced by S into L, and we are having the capacitance, it will be replaced by 1 by SC. Wherever we are, second step is wherever we are having the voltage source VT, it will be replaced by VS. Wherever we are having the current IT, it will be replaced by IS. So after doing these things, we'll be applying KVL, KCL, basic laws to get the equations of the system or the circuit. Then we'll solve these equations to get the ratio of the transfer function, ratio of the Laplace transform of the output to the input, that will be the transfer function. So let us consider this case. This is a phase lag network. It is being shown over here. R1 will be written as it is. R2, it will be written as it is. It is a capacitor. So it will be written as 1 divided by SC. Then this is VT. It will be written as equal to Vs. This is V naught output voltage T. It will be written as V naught S. So we have just completed the first and second step. Then we'll be, in order to get the equations of this system, we'll apply the Kirchhoff's voltage law. When we apply the Kirchhoff's voltage law, then within this we can write down VIS is equal to R1 into IS plus R2 into this is because here it is the open circuit, here R2 into IS plus 1 by C into IS. Then we just do the mathematical manipulation to get the ratio of V naught S divided by VIS. So this comes out to be equal to this, because we have specified the input variable as VIS, output variable as V naught S. So first of all, we apply the Kirchhoff's voltage law to this loop to get VIS is equal to this. And then we apply the Kirchhoff's voltage law to this loop to get V naught S is equal to R2IS plus 1 by CIS, just within this loop. Then from these two loops, when we just divide this equation by this equation, we get V naught S divided by VIS equal to this. So this is the transfer function of the phase lag network. So this is the way we get the transfer function modeling of the system. So next we take up a mechanical translational system. Translational system means a mechanical system in which the motion is taking place along a straight line. So over here, in the case of the in the case of the electrical system, we are having three basic elements: resistance, inductance, and capacitance. In the case of the mechanical translational system, we have three basic elements: spring, viscous damper, and the mass. So their equation can be represented as the opposition offered by the opposing force offered by the spring can be represented as K multiplied by xt. K is the spring constant. Opposition force offered by the viscous damper. This is proportional to the velocity. This is the viscous friction. So opposing force is equal to d multiplied by dxt by dt. D is representing the damping constant. So this is the opposing force developed by the viscous friction, and this is the mass. And the inertia force by the mass is represented as m multiplied by a. So this is equal to m into d2xt by dt square, where xt is representing the displacement, vt is representing the velocity, and that second derivative of xt is representing the acceleration. So whenever we apply the force to a system that is containing these three elements, spring, viscous damper, and mass, then it will be opposed by uh, uh, this. This is the spring force. Then this is the opposing force by the damper. This is the opposing force due to the inertia. So this is the mechanical translational system. So let us consider this system. Here we are having one mass, one spring element, and a damper. Then we are having a velocity of mass, displacement of m in this direction by the application of the force Ft. So equivalent mechanical network, it can be represented as equal to this. So we can very well see that whatever is the applied force, it will be balanced by, it will be opposed by the inertia force, then the opposition offered by the damper, then the opposition offered by the spring. Then we take up the Laplace transform of this equation, we will get Fs is equal to when s square multiplied by m into xs plus s, here its derivative, s into d into xs, then the k xt, its Laplace transform will be k into xs. Then we just take up xs common here, and we get the ratio of xs to fs, so it's coming out to be equal to this. So this is the transfer function modeling of the mechanical system. Here we are having three basic elements: mass, damper, and spring, and the opposition is to the applied force is caused by these three elements. Then mechanical rotational system. In the case of the translational system, the motion is taking place along a straight line. In the case of the rotational system, motion is taking place in the circular manner. So in the case of the translational motion, the displacement is along the straight line, and in the displacement is along the straight line. And in the case of the rotational system, the rotation is along a axis, fixed axis, rotational motion. So in the rotational motion, the displacement is represented by theta t, that is the angle. Then it's in this case the velocity linear velocity is replaced by angular velocity, that is d theta by dt, and the linear acceleration a is represented by the angular acceleration, that is d2 theta t by dt square. Rest is the same. In this case also we are having the spring opposition, friction opposition, and then we are having inertia opposition. In this case, the total torque, and J is the rotational inertia, and in this case, torque is equal to J into d omega divided by dt. Omega is the angular motion, angular velocity, not the motion. So in this case, we have simply replaced linear displacement xt by theta t, linear velocity vt by omega, that is d theta t by dt, linear acceleration at by d2 theta t by dt square, that is equal to d omega t divided by dt. And here force, here we do not have force, here we are having the torque. There we had F is equal to ma, mj was the moment of inertia, and in the case of the translational motion, here we had m, and here we had a. So m was the mass and d2x by dt square was the this element. Here we are having j, and here we are having the angular acceleration, and instead of f, this is equal to t. So this is the mechanical rotational system. Everything is remaining the same, but the displacement is, the linear displacement is replaced by the angular displacement. Now we just take up the example. In this case also, this is a fixed end, and we are having a we are having this is the spring element, this is the damper, then this is the J is equal to 1 kg per meter square. Then we are having another element, another damper, and then another spring here. Then we have drawn the mechanical network over here, and we have just represented the angular displacement theta 2t. We have just first of all we have written the equation over here. T is equal to d2 theta 1 by dt square plus d theta 1 divided by dt plus theta 1 t. So because j is 1 here, then k is 1 here, then also d is also 1 here. So this will be j d2 theta by dt square plus k plus k plus d theta by dt, d is also equal to 1 plus k theta. Then next, here it is minus d theta 2 by dt minus theta, because it's the two more elements are also here. And for theta 2t, this is for theta 1t, and for theta 2t, here torque applied is equal to 0, and this that is used to supply. Here we are having 2 d theta 2 by dt plus 2 theta 2 minus theta d theta 1 by dt minus theta 1 by dt. So here we can see over here that we can write from this at this particular number, theta 2 is equal to this. Then we are getting two equations, this equation as well as this equation. We solve both these equations to get the ratio of theta 2 and t, that is the transfer function of the system. So the procedure is remaining the same. We'll just write down the differential equation describing the system, and from there we can get the Laplace transformation of those equations, and finally we'll get the transfer function. Next is the transfer function of the electromechanical system. So till now we have derived the transfer function of the electrical system, transfer function of the translational mechanical system, transfer function of the rotational mechanical system. Next is the transfer function of the electromechanical system. Electromechanical system, like we are having the motor that is having both mechanical as well as the electrical parts contained within it. So this is an DC. This is a DC motor that comes under the electromechanical system. In this case also we will write down the equations, and we'll take up that will be describing the dynamics of the electrical system as well as mechanical system. So electrical system is represented as back. So this is the armature controlled DC motor. So for this, the back EMF is represented by K into d theta divided by K into omega t. So this is equal to d theta by d. This is equal to, here we should get a K, sorry. So we just take up the Laplace transform of this. So VBS is equal to, here we should have KB, KB into S into the theta S. Then This is the back EMF equation for the back EMF. Then we just applied the Kirchhoff's voltage law to this loop. We'll get ES is equal to RAS IAS plus SLA IAS plus VBS. Then we substitute the value of VBS from here into this equation. So we'll get the equation that is written over here. This equation we'll get after making substitution. Then mechanical equations are Ts is equal to Kt into IAS. So IAS is equal to 1 divided by Kt Ts. So, and this is just from this equation, we can write down this equation. Then we'll just make up the substitution within ES. So we'll get the value of this ES. So then also we have the mechanical equation can also be written as equal to this. So we just combine all these together and get the value of Laplace transform of theta s to the Laplace transform of Es. So this is the overall transfer function of DC motor, that is armature control. So in this way, we can get the transfer function of any system, whether it is a electrical system, or it is a translational mechanical system, or it is a rotational mechanical system, or it is a electromechanical system. So within next lecture, we'll study the other type of modeling of the system. But um, I just finish it over here. Thank you so much with me. Thank you so much.